This conference will now be recorded.
Okay, let's get things rolling. I've got a couple of questions ready to go. The first one that was asked about was it was a multiple choice question number 5 on review packet number 2. It's this one right here. I assume that you guys can see this on your screens. I'm sharing the PDF. Um, this is a kind of a classic conservation of mechanical energy question, and there's so many different ways of doing a question like this that you should plan on seeing at least one of these, not only on your Unit 4 exam, but obviously on the exam in May as well. There are just so many different ways to kind of dress this up. So ultimately, it's a conservation of mechanical energy. There are no external forces acting on the system. In this case, it's a spring mass. So I'm going to just make a little kind of sketch of this. You're going to see these types of questions when we get into Unit 6 topics as well. Unit 6 is oscillations and waves in simple harmonic motion. And so we have this kind of spring mass system where the spring has some coefficient of elasticity K, and the mass of the object in the system is m in kilograms. And we'll say that it's initially, it's on this frictionless surface. It's initially at equilibrium, and then, somebody or something comes along and pushes this in. So now the mass is here, and when we let it go, if this is the center of that mass, I'm going to use some new language. You wouldn't need this language to solve a conservation of energy problem, but I'm kind of pre-teaching, if you will, some of the oscillations and waves topics. If this is the equilibrium position, let's call that the rest or position 0, then the maximum displacement that we push it to one side would be called the amplitude. I think it's a word that a lot of people have heard before. So nonetheless, this mass gets pushed over to the left, and the maximum displacement from the equilibrium position is kind of negative A, or the amplitude to the left. And then when we let it go, it's going to pick up speed, and it's going to be going fast when it gets through the equilibrium position. And then it's going to start to slow down as it approaches the amplitude on the other side. And it's basically just going to bounce around between A and negative A, kind of back and forth like this. So we don't have to recognize that this is a harmonic oscillator. We can simply just look at one of those instances. Let's just take a look at moving from position 1 to position 2. Now we should recognize that all of the energy at position 1 is stored elastic potential energy. So let's say that the energy at 1 must be equal to the energy at 2 because there are no external forces acting. Therefore, I can say that the energy at 1 is 1/2 kx squared. So the displacement from the equilibrium position in this case is not x as it normally is represented, it's d. So we're going to have to make a substitution eventually for x. And then over here at position 2, it's all kinetic energy, and so therefore I can just write that out as 1/2 mv squared. Now the 1/2s go away. I'm going to make my substitution for x. I'm just going to call it d. And I'm going to divide both sides by mass. So I get kd squared divided by m is equal to v squared. Of course, I'll take the square root of both sides. And that's where I get choice E from, right? So the d is squared. When I take the square root of both sides, it just becomes d. And I get root k over m as my expression for velocity. So Dylan, make sure I've answered your question on number 5. I definitely would say that this kind of a straight conservation of energy analysis is something you should absolutely plan on seeing. Also, can you guys just in the chat box, for those of you who are here, I want to make sure the volume is okay, that you can hear me fine, that it's not too quiet or too loud. All right, while you guys are responding to that, I'm going to take a look at question number 24 in review packet number 2. Okay, so question number 24 in review packet number 2 is something that we looked at. I think it was in the 4B class today we saw it. So imagine for a second we've got a trampoline here, and we have this kind of gymnast who is, maybe standing off on some platform here, and he or she is going to start from rest and accelerate towards the trampoline, and right before they make impact, they're going to be going pretty fast. This falling distance is given to us as 4 meters. So we could just use, straight up kinematics and figure out how fast, they'll be going when they fall the 4 meters. And then when we do that, then the question is, well, what is the average force that this trampoline exerts on the gymnast? So the gymnast is going to stretch the trampoline to some kind of secondary position here when whatever that distance is from the blue version to the red version, that's we can call that D, or we can call that X, even though this is a vertical displacement. And so this is a momentum problem, really. The gymnast has an initial momentum before hitting the surface. The initial momentum would be equal to mv naught, where v naught is the speed right there, right before impact. And as this thing is stretching, this might be the final momentum, which we know is going to be 0, because eventually they stretch this thing to its maximum displacement and they stop moving. So we can find a delta P here by, of course, subtracting final minus initial. And in this question, one of the keywords in it is the idea of an average force. So the word average force implies immediately, it should elicit impulse, right? So impulse, by definition, it's a vector, it's force times time, and that's equal to a change in momentum, which is also a vector. So we're going to take these two pieces right here, force and time and the change in momentum, and we're going to see that we're missing a critical component. We have the mass, delta P, by the way, we could also write as m delta V, or if we wanted to be really formal about it, we could say mv final minus mv initial. Any of these kind of versions of the change in momentum would work for us on the right-hand side of the equal sign. We have the mass that's given to us in the problem. So we have that, and we know the final velocity is 0, and we could figure out what the initial velocity is 0. So the right-hand side of this thing checks out. The left-hand side, however, does not. We don't know what the force is. By the way, that kind of use of the word average force is pretty unique to impulse momentum problems. And not only do we not know that, that's what we're looking for, but we also don't know the kind of contact time here, the amount of time the gymnast is in contact with the trampoline. So we really have two unknowns and no way to rectify that. And so that's where choice E comes into play. We need to know the contact time. If this was a really, really fancy trampoline, I don't know, if trampolines get fancy and expensive, I assume that they get bigger and stretchier. So, if that same person stretched a much larger distance here like this, then the amount of time that they're in contact with the trampoline to have the same right-hand side of this equation, meaning the same change in momentum, if we don't want to change that, meaning whatever their final velocity was here, if we don't want to change the change in momentum, then by increasing the time of contact, we decrease the force of impact. And so that's really kind of some critical understanding for impulse and momentum. But I guess the takeaway here is the verbiage of average force. Once you see that, you should be like, okay, we're talking about impulse here. All right, so make sure that I've answered your question for number 24, and we'll take a look at number 11, which is queued next. Okay, so this one reads, we have a delivery man, and the delivery man is going to move 10 cartons from the sidewalk along a 10-meter ramp to a loading dock. which is a certain distance above the sidewalk. So if I were to make a sketch of this, here's one of those cartons, and they're going to move it up this loading dock to to this upper position. And the upper position, we're told, I'm going to cue you to the answer here. I'm going to call that a height h, 1.5 meters above the starting position here. So we should recognize that the stored energy of the box as it moves along this ramp, remember that the ramp is 10 meters. If we wanted to, we could calculate theta because we have two sides to this right triangle. But in this problem, we're given the mass of one of them, and then we're being asked about the total work by the delivery man. Let's remember, we can think of this in terms of a work energy bar chart, or where we started our conversations about work and energy with this kind of bucket analog, right? So what kind of energy does the box or carton that possess at the bottom? Well, it doesn't possess any. It's not moving. There's no there's no kinetic energy. There's no springs here or elasticity involved. And if we're calling the starting point 0, then there's no gravitational potential energy. And when it gets to the top, it's got some gravitational potential energy that it didn't have before. And so then how do we get a change in the amount of stuff in the bucket? Well, we must have done some work on it, right? So that's why, we get these different states of the amounts of energy in the bucket is through work. So I can just look at the change in gravitational potential energy for one of these cartons, and that will tell me the amount of work. Now, remember, I alluded to this at the beginning. We could think of it in terms of a work energy bar chart. I'm kind of running out of room, but I'm going to try writing it here. Remember, those things said, okay, well, you have gravitational potential energy and kinetic energy on the left-hand side. I'm going to leave out elastic potential. And we have gravitational potential energy and kinetic energy on the right-hand side. Well, the box is never really moving. Yes, it's moving at a constant speed as it comes up, but at the final position here, at let's call that the upper or position 2 and the lower position 1, it's got no kinetic energy in either of those places. There's no gravitational potential energy at the bottom, and then all of a sudden at the top, one of those carts has a certain amount of gravitational potential energy that we can find from MGH. So I have 25 times G, which is 250. And so I also have to multiply it by 1.5, which is going to be 375 joules. So there's 375 joules of energy here. This number is 375. That's the same as this number here. That's the amount of stuff in the bucket. That means that 375 joules of work from this external agent must be applied to the carton in order to change its energy. Well, that's, of course, the work done by the delivery man. There are 10 boxes, and that's where choice B comes into play. Make sure that I've answered your question on number 11. So Constantine, I appreciate your question. And before we had, before this thing kind of started, I scanned the questions from the online quiz, and I could not find anything referencing internal versus mechanical energy. So if you could provide a little context, I would appreciate it. Either, screenshot maybe on the quiz, or if this is from the review packet, you can identify it with a number. If you screenshot it, you could email it over to me, and then I'll be able to kind of figure out what question you're talking about. Okay, so Connor's saying, all right, so there's a question, a boy pushing the cart at a constant rate. Is that on the quiz, on the online quiz? Because I'm going to look that up if it is. All right, I'm going to change I'm going to change the screen you guys are seeing, and I'm going to change it over to Chrome. So you should now be able to see the quiz. Again, I'm assuming that you can see the quiz, and now I need to find this question about a boy pushing a cart at a constant rate. Okay, give me one sec. I'm panning. One of the kind of things that makes this difficult is that they're all like mixed for us. Oh, number 2. Wow, I went past it pretty quickly. All right, here we go. Okay, I see what you're saying here about internal energy. Okay, so let's take a closer look at this one. A boy is pushing his wagon at a constant speed along a level sidewalk. So we know that the sidewalk's level. The graph below represents the relationship between horizontal force exerted by the boy and the distance the wagon moves. So there's this kind of constant force and a constant velocity. The force that's applied is overcoming, friction. It must be friction. So they want to know what happens to the wagon's energy. Well, I have a couple of initial reactions. For starters, there's so everything's horizontal. It's a level sidewalk. So I don't like the gravitational potential energy increasing or decreasing, because that would require a change in height. So I don't like answers 1 and 2. I'm guessing that the best answer is number 3. I don't know if you guys have already given an answer here, but let's make a quick sketch, and I think I can explain. So I believe that in this instance, the use of the word internal energy refers to heat on the axles here, right? So these go across to other wheels over on the other side of the wagon. And I think what they're trying to get at is that how is it that you could apply a constant force? There's no sliding friction, right? Because this wagon isn't being, the wheels are rotating. It's not skidding across the surface. So the question is, well, what's happening to the work that the person's putting into this, right? So the area under this graph here is work. We can see that it's 6 times 30. So for the first 6 meters, the boy applies 180 joules of work to the wagon. Yet it's not net work because the kinetic energy isn't changing, and therefore, the thinking is that the internal energy of the system, the heat in the bearings and things like that, has to increase by 180 joules. So that's question number 2, at least on my quiz, and that's how I would answer it. Minimally, I would eliminate 1 and 2 because of the level surface, which makes it a 50-50 question. I know that's not satisfactory, but this is a question about what's happening to those 180 joules, and it's increasing the temperature of the axles. All right, so thanks for finding that. Hopefully that answers your question. There was another question that had queued, and so I will find it. It's review packet number 1, question number 4. So I'm going to bring that up. I'm going to change screens. All right, so I am back to sharing the PDF, and so I want to find the next question. All right, so question number 4 is we have a force of 10 newtons stretching a spring. The spring constant is known as 20 newtons per meter. They want to know the potential energy stored in the spring. So I can say that, by definition, potential energy in springs, or elastic potential energy, is 1/2 kx squared, where k is the spring constant. In this problem, it's 20 newtons per meter. Of course, 1/2 of the number 20 is 10. And then we have to multiply it by the oh, I see. We have to multiply it by x, and x was not, we have to multiply by x squared. X was not explicitly given to us in this problem, but they did tell us that we applied a force of 10 newtons. And so therefore we have to employ Hooke's law. This is a kind of dynamics redux, if you will. You might remember that, sorry, that's not negative. A spring force, by definition, is negative kx. And so the negative sign just reminds us that the direction of x has to be opposite the direction of the force. So if we pull to the left, the spring force or the restoring force from the spring will be to the right. Anyway, if we pull with 10 newtons and the spring constant is 20 newtons per meter, then we can see that the displacement in this case is 1/2 of a meter, or 0.5. We're going to need that information to answer that. And so we're going to plug in 0.5 meters squared. That we get 0.25 times 10, and that's where 2.5 becomes our best answer. Make sure that I have answered your question for multiple choice 4 on review packet number 1. Let's take a look at question number 18. Um, 18 is, again, kind of a classic. It's a classic Unit 4 question, and the reason is the College Board really likes to ask questions comparing the momentum and kinetic energy of an object. And the reason is, just so that you see this with clarity, we can see that momentum is dependent on mass and velocity, but so is kinetic energy. But momentum is dependent on is directly proportional to velocity and mass, where kinetic energy in this case has not only a coefficient here, but we can see that it's proportional to speed squared. And so that's going to create kind of some interesting phenomena, right? So if I double the speed, the momentum doubles, but the energy it possesses increases by a factor of 4 because that's squared. So let's take a look at this problem. We have two objects and they have the same momentum. So, Q can have more kinetic energy than P if, so let's compare the energy of Q and the energy of P, right? This is ultimately what we're saying. Let's compare these two energies. So we're going to have 1/2 the mass of Q times the speed of Q squared. And we're going to set that equal to 1/2 the mass of P times the speed of P squared. So just because they have the same momentum doesn't really say anything about their mass and velocity. It just means that their mass times their velocity is equal to each other. So we can see that if Q has more speed, then even though the mass might be less, right? So I'm analyzing this for object Q. If it has more speed, the mass might be slightly less. Let's kind of just use the number, 10%. So if it has 10% less mass by comparison and only 10% more speed, it's still going to have the same amount of momentum. But because this is squared, then it can have more kinetic energy. And so that's basically what this problem is teasing out, whether you're able to see the effect of the kind of exponent on the speed variable for kinetic energy. Hopefully that answered your question. It's a bit cerebral. There isn't like, I think it's a little hard to see that with crisp clarity, but nonetheless, that's what we have. Hopefully I've answered your question on number 18. I am doing FRQs. So let's take a look at packet 2, FRQ number 3, part F. All right, FRQ number 3. All right, so we have this rover. We're being asked some questions about it. So let's go down here to F. I can see how this question creates some problems. For starters, let's read the question again just to familiarize ourselves with it. We're given some data. We're given how much energy it has. We're told that it takes 10 watts for driving under average conditions. We're given the speed that it can go. This is all from an early Mars rover. You guys, this is 1997, so you guys have been alive for some pretty sensational ones. I think the most recent one was called Opportunity. It was about the size of a car. This one is more of a toy. So this question says, all right, well, suppose that 0.01% of the power for driving is just expended against atmospheric drag. So what's the drag force? Well, the key to unlocking this question is here in these first few steps. This expression, force times velocity, is not given to you in the problem, or sorry, it's not given to you on your yellow equation sheet. This is power is equal to the rate at which work is done. That's given to you on your yellow equation sheet. And we know that work is equal to force times distance. So all we did was replace the numerator. Instead of work, we replace it with force times distance. And we know that distance over time is speed. It's a rate. It's the rate of change of position. So this kind of last expression that I've double check marked is a useful one. It's a useful expression for power, especially when the object is moving at a constant speed. If you ever get a question about power and the object's not accelerating, this is often the direction that you're going to go in. So we know the power that's being used. That's the 10 watts that we were given. We know the speed that it's going. They gave it to us. So we can figure out really how much force the vehicle, if I draw this as a free body diagram, in order to move at a constant speed, the vehicle needs to produce a certain amount of forward force to compensate for this kind of drag force acting to the left. You know, I can call that subscript drag here if I want to. And so there we go. We have an expression, and you can see that we kind of rearranged this and solved it for the force from you know, from all resistive forces. This could be, you know, I'm calling it purely the drag force, but it's from all, you know, whether it's drag and friction, et cetera, et cetera. So we get this number. This is the total of all of the of these forces. You know, roughly 1,500 newtons. And here's where the 0.01% comes in. This is kind of where I erred when I initially made this. This should be the sum of all the resistive forces, but only 0.01% of that power is used to overcome drag. So there are other things acting to the left, and only drag is only 0.01% of it. So I just multiply this kind of total thing. I can see how that would be hard to see. How did you know that, you know, there are other forces? And I think the only cue there is that they gave you this as a percent. And so our answer then is, you know, we get our answer by multiplying the drag force times that percent written in decimal form. And we get, 1/10,000th, if you will. All right, so our final answer is 0.15 newtons. Hopefully that helps clarify in some way that FRQ. There's a couple other questions here. I've got one on the online quiz about a 15 kilogram object moving at a speed of 7.5, and also packet number 2, question 22. I think I'm going to start with that one and then go to the online quiz. So let's take a look at number 22. Okay, so we have a student. They're initially at rest on a frozen pond. That's nerd speak for friction can be ignored. They throw a hammer of mass 1 kilogram. The hammer moves off in one direction. Let's just call that to the right, or positive v. Let's remember that momentum is a vector. And the student moves off in the other direction. Which of the following correctly describes the above situation? Well, let's just draw a picture. I don't think you would need to draw a picture in order to get this answer correct, but let's just do that anyway. So the student's sitting here and they're holding in their hand a hammer, right? So this is my bad sketch of a hammer. And this is the initial condition. And then some amount of time later, they chuck the hammer. And so the hammer's going to the right, and the student, if there's no friction, has to be going to the left. These amounts of momentum have to be the same. However, the student that's going to the left has to have a momentum that's in the negative direction if we're calling the hammer the positive direction, or vice versa. The whole point is that the momentum vectors add together to still be 0. Let's remember that momentum is conserved, and therefore the sum of the momentum in the system when this all starts is 0, and that's because they're initially at rest. And therefore, when we add up all the different little pieces of momentum after the event, it still needs to be 0. This line here represents, everything above the line is before, and everything below the line is 0. So the momentum can't change. That's a conservation law. So, what can we say about this? Well, if the momentums are the same, the hammer has to have less mass than the person. So it's going to have, compared to the person, a larger velocity. The person obviously has a bigger mass and a smaller velocity. They still multiply by each other to give you the same magnitude of momentum, but the velocity of the hammer is much, much larger. And this relates to a previous question that was asked about kinetic energy, comparing P and Q. Kinetic energy is 1/2 mv squared. We can see the heavy dependency on speed when calculating kinetic energy. And so, therefore the hammer has to have greater kinetic energy than the student, simply because of that velocity dependency. If we look at the momentum statements, we can see that they're really violating conservation of momentum principles with those statements. One's saying the hammer has more momentum, the other one's saying the student has more momentum. Those can't be right. We've discussed that already, because they have different masses and velocities, but the simple products of those give us the same magnitude but opposite direction. We can see the two energy statements with C and D. And then this one is incorrect because it doesn't recognize the heavy dependency on velocity for energy. So C is the best answer here, simply because it has to be going faster. Hopefully I've answered your question on number 22. I'm going to bring up a different screen. I'm going to bring up the Chrome browser and we'll take a look at that. I think I shared the wrong thing. All right, let's try this one more time. All right. So you should be seeing the online quiz. And we want to find this question about a 15 kilogram object moving at 7.5. All right, I will scan. I think I see it, number 18. All right, hopefully this is the one you're talking about, right here. So we have an object that's moving at 7.5 on a horizontal frictionless surface, and they want to know the total work to increase its speed. So the work energy theorem at the end of the day says that if you do any leftover work, it's going to change the object's kinetic energy. And we can see that the kinetic energy is going to change because it's getting faster. So we're trying to answer the kind of work question. All we really need to know is the difference between the final kinetic energy and the initial kinetic energy. So this on the right-hand side becomes 1/2 mv final squared minus 1/2 mv initial squared. Well, we have all these numbers. I could factor out the 1/2 and the m. We might as well. It's 1/2 of times 15 kilograms. And then we're left with v final squared minus v initial squared. Well, that's 11.5 squared minus 7.5 squared. And so we have everything that we need to find the change in kinetic energy. 1/2 of 15 is 7.5. It's still kilograms because the 1/2 is just a coefficient. And then we're going to get meters squared per second squared when we square this. I don't have a calculator with me, so I'd have to plug that in my calculator, multiply by 7.5, and hopefully we can get the right answer on question number 18. Hopefully I've answered your question on that. If I haven't, please ask a follow-up. And I think at this point, I have caught up to your questions. I don't see any ones that I haven't gone over. All right, so I'll give it another minute or two. If you do have other questions, I will wait for them. Question number 3 on packet number 2. I'm going to change gears again. This is the question that some students have asked me about over the last like 24 hours. I'm not surprised to see a question about it. So there's a ball, the ball's thrown vertically upward, so it's got some large initial speed. And then it gets to some maximum height here where that final speed is 0 when it reaches its maximum height. If we're looking at this in terms of energy, we can recognize that when we started, there was no gravitational potential energy, if we're calling this 0. And when it gets to height h, all of the energy is gravitational potential energy. We could find out what it is if we wanted to. It would just be mgh. So at some position halfway up, h is just half of what it would be. So the gravitational potential energy is mg times h over 2. So it's half, right? Like, I mean, hopefully we can see that if this were a bucket, half of the energy here would be gravitational potential energy. And when it was at the top, all of the energy in the bucket is gravitational potential energy. And at the bottom, the bucket has no gravitational potential energy. Conversely, when I take a look at kinetic energy, it's all kinetic energy at the bottom, and it's only half kinetic energy at the middle, right? If the total amount of stuff in the bucket, I'm making up a number, let's call it 10, then if we have half of this it is gravitational potential energy because of the h/2 dependency, then the other half is kinetic. So I should be able to recognize that at the halfway point, the kinetic energy is going to be half of what it was when it started. So it has to be either A, B, or C, and cannot be D or E for that, for that reason. Now we have to answer the velocity question. And I think that this question could be best answered by writing it out as a proportion. I'm going to say that the final kinetic energy, I'm going to describe it as a ratio and compare it to the initial kinetic energy. And I can say then that the final kinetic energy is 1/2 mv final squared, and the initial kinetic energy is 1/2 mv initial squared. I was told in this problem, or I wasn't told, we deduced that that the ratio of final kinetic energy to initial kinetic energy is the ratio of 1 to 2. Right? We've established that already by saying that when it gets halfway up, it's got half of the energy that it started with. I could write that as just writing 1/2 in the numerator and 1 in the denominator. Or I could say that the initial kinetic energy is twice as much as the final. Either of those will yield the same ratio of top to bottom of 1 to 2. And then the 1/2s cancel out, right? I'm kind of comparing the right-hand side now. The 1/2s cancel out, the masses cancel out, they're the same, that hasn't changed. And so I'm left with, 1/2 is equal to V final squared over V initial squared. Well, I'm looking for V final, so I'm going to multiply both sides by VO squared. Now I get VO squared over 2 is equal to V final squared. And I think you can see where we're going from now. We take the square root of both sides, and I get VO over root 2, which is our choice B. Hopefully that answers your question there. Let me know if you have follow-up questions. Packet number 2, multiple choice 23, let's take a look at. So question 23 has something that should interest you, and that is there's a couple of keywords here. It's this one right here. As soon as you read that, they're saying, okay, I'm reading a question about force and time. I know the weight and therefore the mass of the object. I know the change in velocity, so I know the change in momentum. I think I can answer the time question. This is an impulse momentum problem. I can say that impulse, which we know is force times time, I'm going to leave out my vector rays, is equal to my change in momentum. And the change in momentum is equal to m times delta v, or I can write that as m times v final minus v initial. And so I'm going to pay attention to this term and to this term, because that's all stuff that I have. I have the force. It's 2.4 times 10 to the fourth. So I have that. I'm looking for time. Mass, I can get from the weight, right? I can divide that by G, or just divide it by 10, and I get 1.5 times 10 to the third kilograms. And I know the final and the initial velocities, so I'm good to go, right? Like, it's scientific notation, so it's a little obnoxious, but everything here is known. So T is equal to m delta V, all divided by F. And I'm ready to go. So I plug those numbers in, and hopefully you get 1.5 seconds when you do that. Make sure that I've answered your question on number 23. All right. I have one more question here. It looks like it's number 15 on packet number 2. So, so 15 is a great question. It's a great question just because it's kind of down the middle and something that you'll see. So, I'm going to make a sketch. Let's say that the wall is here and we have a ball. Again, these bouncing questions are very common. Again, because most students forget the vector nature of impulse and momentum. So the ball has an initial speed of 6. Let's say it's moving to the right. So we'll call that positive. And it collides perpendicularly with a wall and bounces off with a speed of 4. So whatever we want to call this, 4 meters per second, it has to be negative. That's the key. That's the question that's the issue that people will make mistakes with. They're going to call a novice physics student, the mistake that they'll make is call the delta V 2. So we're looking for a change in momentum. And the reason we're looking for a change in momentum is because the change in momentum is related to the impulse delivered via the impulse momentum theorem. So that's what we're being asked about in question number 15. What is the impulse? Well, we know the impulse if we can answer the change in momentum question. So that's going to be m times v final minus v initial. So the mass of the ball is 0.5 kilogram that was given to us in this question. And if I was formal about writing this out, I get -4 meters per second minus 6 meters per second, which is going to give me -10. And that makes sense, right? The impulse was delivered to the left. How do you get something going to the right to go to the left? Well, you give it an impulse or a force to the left. And so 0.5 times 10 gives us 5 Newton seconds to the left, but they're only asking the magnitude question. And so that's where we get answer C from. Hopefully I have answered your question. I think we're going to wind down there. That will end the first of 2 review sessions. I'll do another one tomorrow to take any questions that might come up as you guys are preparing. So there we have it. Thank you very much, and I will see you tomorrow.